You know, I have mixed feelings about this because I'm very excited about establishing new baseline standards for the science of precision shooting. But I also know deep in my heart no one will follow them and I'll continue to shoot 5-shot groups. But for the record, you are all wrong. If you're like me, you like science and you hate stats. That's not true, I love stats. But stats is hard and science is hard. For example, let's say you have two flavors of 22 long rifle ammo. You've got the Norma subsonic, or you have the SK rifle match ammo, and you want to know which one is more accurate in my gun. Or if you're a hand loader like me, you probably have a giant pile of targets like this. This is my 6 PPC, and I shot a 5-shot group with 27 grains of Varget, with 28 grains of Varget, and what the heck, with 28 grains of Varget. It was probably 28 and a half. I can't remember. This was a while ago. And I also shot the same thing, increasing with H4895. And I shoot these little groups, and then I measure them, and I write down the measurements, and I say, ooh, this one's smaller, so this one must be better. If you're watching this, you've probably done the same thing in some form or another. I'm here to tell you it's wrong. There is no significance to this. You might as well be rolling the dice to see which one is better. So, how do we know this? Let's go to my Lappy 2000. Okay, so we wrote a special piece of software to help us understand this question. This was originally written to understand effect size, and we made a fun discovery. So if we take a look in here, this is meant to simulate dispersion. So when we say dispersion, that means every single bullet is not going through the exact same hole. They disperse and you get a group. And so the way this tool works is I have variable A, and the standard deviation is 1 on this. And I click the draw button, and it starts at the center, and it picks a random direction. And then this is an important part. Listen close. It is random normally distributed length. You don't know what that means either? Cool. So let's keep drawing for a little bit. So we're just going to draw a whole bunch of these, and you're going to see that they're kind of tightly clustered in the center here, and as you get further out, they're more sparse. Let's skip ahead, and let's just go ahead and draw 100,000 of them. So this is what's called the bell curve or the normal curve. So when we say normally distributed, that means we're using this distribution. Or in other words, in this green section, our 50% of the shots are within this distance from the center. The blue section is 95% of the shots, and then the red is the remaining 5%. So now you know everything there is to know about normal distributions. So let's clear that out. And let's add in variable B. And let's say this has a standard deviation of 0.5, and so does B. So we have, previously our standard deviation was 1. You can see that was what we got. Now we have 2 standard deviations of 0.5. So if I hit the draw button, well, that was tiny. Changing these to 1s because they're too tiny and you can't see them. All right, so we did the same thing with variable A. We start at the center, we go out a random normal distribution distance. And then we arrive at this point, we do the exact same thing, random angle and random distance. And let's keep doing that, and you can see a few examples of how these add up. Let's cut forward, and if I do 100,000, SD of 1 plus an SD of 1, is not an SD of 2, that's an SD of 1.4. And the important thing here is, you remember what the curve looked like before. It's missing the middle. It's no longer a normal distribution. For the readers at home, you've probably already guessed, yes, this is a chi distribution with degrees of freedom equals 1.6. It was my first thought as well. However, this is merely a simulation. So what we need to do now is go out to the range and shoot some groups. We're going to shoot 100-yard groups, and then we're going to come back and see, did our 100-yard groups match our expectation. All right, it is a beautiful spring morning, and we are at the range with a whole bunch of guns, and Today we're here to prove that group dispersion is not normally distributed. So what we're doing is we're shooting 100 shot groups with every rifle we have and with multiple types of ammo for some of the guns. And we're going to load an image of the target into the software, identify our aiming point and every single bullet hole, and then we're going to run a whole bunch of stats on that. The main one for just proving our point today is doing a histogram to see that, sure enough, it is not normally distributed. First up, we have just the classic Ruger 1022. I've got a Nikon, I think it's a fixed 4-power if I remember right. And we're just shooting the crappiest ammo I had on my shelf. And we're just going to start with this. And we're going to shoot 100 rounds on paper. Damn, it was a lot worse than I thought. Also,
you never cleaned the gun, did ya?
What's that?
You've never cleaned that gun, have ya?
Don't judge me. Yeah, my main comment is I don't do a lot of cardio, but the more important thing is it looks like we got all, or at least most of the shots, and for my untrained eye, I'm going to call it not normally distributed, but we'll see what the computer says. All right, this is my beloved 22. It is built off of a CZ 455. Forgot what action it was. I've got a Lilja match grade barrel on here. This is a Citron 50 power scope. I put in the, I forgot who makes that trigger upgrade kit, but that's in there. The trigger is really light. Carbon fiber stock that I made myself and never finished, so it's pretty rough, but this gun shoots really well. So we're gonna shoot a couple flavors of ammo out of this and see how it does. We've just shot the CZ with the Norma subsonic ammo, and fun thing I want to note is these are the flyers, so there's a 2% chance of this gun having a flyer. This was the first shot group, and we were worried that they were getting too tightly clustered and we wouldn't be able to pick out the individual shots, so we moved to a second group, but that's not a big deal. The software will combine them together. We're done with the custom 22. We've shot the Norma from it and the SK match ammo. Probably do our 223 next. This is a very beloved gun of mine. This is my prize table gun. I won this action from the Las Vegas NRL Championship in 2000 something. I think it might have been their first one actually. I won this scope at the Night Force ELR Challenge in Wyoming. I won this stock at, I think it was a Quiet Riot in Utah. The barrel came from, let me think, I think that was an Arizona PRS match. The trigger came from a Nebraska PRS match. And this bipod, I think that was actually last year's Night Force Wyoming ELR Challenge. So it's been slowly pieced together bit by bit through prize table acquisitions. And we're gonna shoot a 100 round group with it. So I got this Fiocchi Target Max, just 55 grain FMJs. I suspect it's not going to be very good, but that's okay for what we're doing today because we're just trying to prove the non-normality of dispersion. All right, next up we have the 6.5 Creedmoor. This is also custom built on Remington 700. It's been trued, blueprinted, lapped. Got a Vortex PSD on here. Bartlein barrel, Boyd stock, it's bedded in there. Dual trigger, which probably should have cleaned out. A little crusty right now. Getting a little tighter in precision now, so we're going to start shooting 5-shot groups. And we've got some Hornady match ammo. This one's the 140 ELD match. We're going to shoot 100 rounds of this. Bonus on this one, we're going to track it on the lab radar and test the normality of the velocity deviations as well. All right, next up we have the Desert Tech MDRX. This one has an 18-inch 223 wild barrel and an EOTech EXPS red dot sight. We're shooting green tips if I remember right. This is Nate's gun, so he's going to give us 100 rounds out of this sucker.
Wave to the camera.
It's actually pretty good. EOTech comes zeroed, by the way.
Alright, I'm on Glasgow again. Okay, this is a Colt M4. It is not fully automatic, but it does say M4 carbine on the receiver, so I don't want to hear it. It also has an EOTech EXPS2. It's got a bajillion rounds on it, but it's super reliable. It's a nice gun. The ammo we're shooting today is whatever the cheapest crap gunny's had, which happens to be Igman, made in Bosnia. Thank you, Bosnia. You know, I have mixed feelings about this because I'm very excited about establishing new baseline standards for the science of precision shooting, but I also know deep in my heart no one will follow them and they'll continue to shoot 5-shot groups. But for the record, you are all wrong. I don't know if we should put that in there. The standard in precision rifle shooting is 5-shot groups. For example, you get your fancy new custom built Creedmoor and you went with a 6 Creedmoor instead of a 6.5 because you're a hipster, and you bought your favorite bullet and your favorite powder and you load up a ladder test and you're like, I'm gonna shoot 5 shots of 41 grains and 5 shots of 41.2 grains all the way up to 43.5 or something. What, I don't actually know the range. Whatever. So you're gonna shoot 5 shots of each flavor of powder, and then you're gonna go shoot 5 shots at your target, and then you're gonna use some really, really bad statistical analysis, which probably consists of measuring the extreme spread of every 5-shot group, and then maybe you try and find a flat spot or just pick the smallest group. And you might as well be rolling a pair of dice. Just like, you can save yourself the ammo and just like write down the numbers, 41, 41.2 up to 43 or whatever you're doing, and just roll a set of dice for each number, and then pick the one that has the dice roll the lowest number. Oops, that's a big rock. And that will have the identical effect to going out and shooting them and picking the smallest 5-shot group. What I think we're gonna try and prove, or what I'm gonna demonstrate with our software simulation is somewhere, depending on the effect size you're looking for, 50 rounds is probably a good minimum. If you're looking for a big effect. If you're looking for a very small effect, like the kind of effect you would get from going from 41 grains to 41.2 grains of powder, to be able to identify that effect size, you're gonna need to shoot between 1,000 and 10,000 rounds for each powder measurement. So you need to shoot 5,000 rounds of 41 grains, and then 5,000 rounds of 41.2, all the way up to 5,000 rounds of 43 grains. And if you know anything about precision rifles, you're probably pretty aware that you're gonna need like 10 barrels or 20 barrels or 50 barrels to complete your ladder test and have any kind of statistical significance to it. And nobody wants to do that, and so we just follow what the Colt says, or the dogma of shoot these 5-round groups and do the there's like the Satterley ladder test. No offense, Scott, I love you. Or the Wheeler ladder test. No offense, Alex, I also love you. Thank you for that rifle you built me. It's amazing. However, there's no statistical significance to any of these tests that we're doing. They're complete noise. And so that's what we're trying to establish today. We're trying to establish what does an actual statistical model look like for trying to improve the accuracy of your gun, where you have a control, where you take the gun out and you shoot it in a certain condition, which could be a certain type of ammo, a certain bullet, a certain scope or shooter or whatever, and then you have a second condition where maybe it's a different powder or a different amount of powder or whatever, when you do that and you compare A and B, what do you need to do to actually scientifically prove with high confidence that you made a difference? And that's what we're trying to establish today. And we're doing that with 100 shot groups. And I think what we're going to see is it's going to be really hard to establish significance. We will be able to likely establish significance between, say, a Ruger 1022 shooting crappy ammo and a 6.5 Creedmoor shooting match ammo. We're going to see significance there. We might even see significance between the custom 22 shooting the Norma match ammo and the SK match ammo. Maybe. But if you're trying to find tiny significances, tiny effect sizes, it's essentially impossible to do it. It's particularly impossible with small numbers of rounds. So, rant over. Well, so the thing that we can do with the software is make it easy to run significance tests and tell you is your result. So you can shoot a group with sample A, shoot a group with sample B, and plug it into the computer and say, is there statistical significance? There probably won't be unless it's a large effect size or if it's a really large sample size. Yeah, so like when you go out and you're shooting 5-round groups, the only thing that you can hope to gain from that is if there is something very, very wrong. For example, in some gun setups, if you exceed a certain velocity, well, really when you're exceeding a certain heat, the lead core can start to melt and it rotates within the copper jacket. And if you keep loading your ammo hotter and hotter, you may be able to identify when that happens with 5-shot groups. If you're shooting like little tiny groups and then all of a sudden you're shooting huge groups when you pass a certain threshold, you can maybe identify that with 5-shot groups. But if you're trying to tune or find harmonic variances or some bullshit like that, it's just not there. There's simply not enough data to extract any meaningful information from 5-shot groups. Yeah, they are worthless for comparing small effect size. So things that you can, if you want to test something with a 5-shot group, if you want to test like the difference between how well you can shoot standing and shooting freehand versus how well you can shoot prone, 5-shot groups are going to tell you that those are different. If you want to compare a bench rest rifle, like most accurate gun in the world, to your dad's 30-30 lever gun, 5-shot groups are going to help you identify that. But you need massive effect sizes for 5-shot groups to tell you anything. So most of the time they just give you warm fuzzies that, oh, look how tiny this group is. But in reality, once you overlay all of your 5-shot groups, you're going to find that it wasn't tiny. It was just like, somewhere in the cluster of, for example, the Creedmoor I shot today, I shot 20 5-shot groups to get 100 rounds on target. And some of those groups are massive. Some of them are tiny. And it doesn't mean anything. It just happens to, once we overlay all of those groups together into one 100-shot cluster, you're going to see that it's a very uniform cluster. There aren't flyers, or maybe there's like a flyer. Sometimes bad bullets get through production, but like these big groups are not anomalies. The big groups are just going to fit right into the cluster. And when you're looking at the 100-shot group, you won't be able to identify, oh, this was that tiny group and this was the big group. They're all just going to look like a big cluster. So when you're shooting 5-shot groups, you have a big cluster of where they could go, and you're just picking 5 random points in there, essentially. Alrighty, so we went to the range. We have 8 targets, each with 100 shots on target. We have a brand new piece of software here. Let's load up our first target, which we shot with a 1022. So this is the Ruger 1022 with just Federal crap ammo. No offense, Federal, but your ammo is crap. And so we've indicated on here the 1-inch measurement for our scale, and then our aiming point. And then we've put on here a marker for every single bullet hole. We've got 100 bullet holes on here. We can zoom just a little bit and see what the shape of our group looks like. And it just kind of looks like a bunch of bullet holes. Is it normally distributed or is it not? Well, let's look at the histogram. And this green line is a normal distribution line. And these two red lines are the distribution that we predicted based on the previous software. And you can see the real life data matches our prediction. It is not normally distributed. The dead center is the least likely place for a bullet to go, and somewhere around this first circle here is the most likely place. And then this outer circle is the 95th percentile, where 95% of all shots should land inside of there. Sure enough, we were right. We were not right. Science was right. The simulation was correct. The real world data acted exactly like predicted. We want to answer the question of which ammo out of these two shoots better in my gun. Which one's more accurate or produces the smaller groups? Okay, so we went out and we shot these two targets. This one's with the SK, this one's with the Norma. There are 100 shots on each of these pieces of paper. Alright, so we are going to first load up the Norma into here, and somewhere on this paper, oh, here we go. Here is one of the groups. So we've indicated our scale, our aim point, and then every single little hole. And then over here, same thing for the aim point for this group, and all the little holes. And we have a scatter plot here showing where they all went. And again, distribution, or a histogram showing the distribution. It matches the model we predicted. We do the exact same thing for the SK. We've marked our aim point, our scale, and then every bullet hole for all of the groups. There's the other one, and then there's one more. And once again, they're smaller this time. Yeah, so the SK produced a smaller extreme spread on the group. But is it significantly different, or is it just dumb luck? If we come down, we get a histogram again, and we get to the bottom, and that's right, we ran the Mann-Whitney-Wilcox U-test. And we found a significant difference. We're highly confident that the SK is more accurate than the Norma. So next, let's do another example of... Okay, so the last one was fairly obvious. This one's maybe less obvious. We've got the MDRX 100 round group, and we have a Colt M4 100 round group. They look kind of similar. Let's plug them into the software and see what it says. So we've got M4 with the Igman Bosnian ammo, and the MDRX with the same ammo, same shooter, same optic. And we can zoom out a little bit and see the Colt is a little bit bigger than the MDRX, but is it significant? And so we go down, and everybody, yeah, I know, I don't remember either. No significant difference found. And so that is the power of this tool. Usually you would just say this one's smaller, so it must be more accurate. In this case, we can actually use science to say there is no significant difference between these two systems. So if you went and shot 1,000 rounds out of each one, maybe you would find a significant difference. But no way to know without doing that. And honestly, if you can't tell in 100 rounds, from a practical standpoint, you probably don't need it. Let me throw in one more example. So we shot the Creedmoor, and the main reason I want to bring this one up is because this one has a significantly smaller amount of dispersion, or in other words, it shoots smaller groups. And we want to confirm that with a precision rifle, a match barrel with match ammo, do we still follow the same distribution? And here's our group. You can see it is a lot tighter. And once again, we're following the same pattern. We're not likely to hit in the middle, which if it were normally distributed, this middle peak would be the most likely place. And I would just cut the center right out of the target. But that's not what we get. And then we can also compare that to our 223 bolt gun. High-end gun, low-end ammo. The groups are fairly different. It's not wildly different, but it's clearly a lot bigger on the 223. Same distribution model, and in this case, there is a significance. P is less than 0.05. Okay, I forgot to explain root mean square. Okay, so we have our norma and SK, and we can see that the SK shoots smaller than the norma, and additionally, with science, we can confirm that there's a significant difference. How much of a difference should it make? So we have on one side the norma, on the other side the SK ammo. The standard deviation is smaller on the SK than the norma. We have found with science that there is a significant difference between the two with a really high level of confidence. P is less than 0.05. P value is basically you have a stats equation and you pour a bunch of numbers into it and it gives you a P value, and you don't really have to know what that means unless you're a statistician, but the thing you can know is it ranges from 1 to 0. If it's like 0.5, that means there is absolutely no significance to the data. The scientific standard among the scientific community is if P is less than 0.05, then we call that a 95% confidence. In this case, P is 0.00015. So it's tiny, so we're extremely confident that we got the right answer in this case. What is the effect size? So this one, your average 5-shot group over like 100 groups is going to be 0.77, or about 3/4. And this one, with the SK ammo, is going to be just over ½ an inch. Does that mean that this norma ammo is a 1/4 MOA worse, or it has a 1/4 MOA additional error? The answer is no. And we use the root mean square method. The root mean square method is defined by, we don't really give a crap, we just know that you just push the numbers into the statistics machine and it gives you a value. And we don't really care how it works right here today. The value it gave us is 0.56. How does 0.77 minus 0.562 equal 0.53? We have removed over ½ an inch of error from a 3/4 inch gun. So you would think it goes to a 1/4 inch gun, but that's just not how it works. If we go back to our little simulator here, we have 4 variables, each with a 1/4 inch of error. And if I just skip ahead and draw 100,000 of these, our standard deviation is 0.5. So variable A will give you a 1/4 inch of error normally distributed, but then B might cancel that out by going in the opposite direction. So A sends you high and right, B sends you low and left and cancels it out, but then C might go up and then D goes down, and so you add them all together and it turns out to be a half. But if I subtract a 1/4, we're going to do this again now, and it was a half and now is 0.433. So a half minus a 1/4, in this case is not a 1/4, it's 0.433. So bringing this all together, if I do a hard refresh on this now, this is our current working model for the errors contributing to dispersion. So in other words, if I have a really nice gun and I put the crosshair on the same place every time I pull the trigger, why does the bullet not go through the same hole every time? That is the question we're trying to answer. The answer is there's a lot of things, and here is a list of candidates for things that are partially understood or well understood or maybe not understood at all. And we may add to this list in the future, but this is our starting point. If I go ahead and just run this 100,000 on this guy, we're going to see our average 5-shot group is 0.7. Now, in a future video, we are going to be testing a system to try and completely remove the mechanical error. So if this was 0.7 for 5-shot groups, and I change this to 0 by completely removing that, now it's gone to 0.55. However, you need to shoot an absurdly large number of groups to confirm that. As we've seen, we needed 100 shots through an M4 to compare it to an MDRX and get no answer. So the question is, how many shots do we need? You may have noticed we haven't used this part of the page yet. So let's do it. So I'm going to change this to 1. to start with. And I'm going to change this back to 0.2, and I'm going to check this box. And when I check that, what that tells the simulate button is we are going to do 20 shots. We're going to put 20 bullet holes on here, and we're going to get our standard deviation, and then we're going to set this to 0, and it does it in a blink of an eye, so you can't really see it. We're going to set it to 0, and it will do it again, and it will compare them and tell us, for trying one time, how likely are we to get the right answer. And with one try, in this case, 0% chance. So let's set that back to 0.2. But if we try it 100 times, so this means we're going to go to the range, we're going to shoot 20 shots with the control setup, and then we're going to switch our gun to a different setup. We're going to shoot 20 more shots, and we're going to do that 100 times. So we're going to shoot 20 shots, 20 shots, that's 40 total shots. We're going to do it 100 times, so this would be 4,000 shots. What is the likelihood that we're going to get a right answer? We get the right answer 38% of the time. If we immediately follow it up with a second time, we have a 14% chance of getting the right answer a second time. So obviously those are abysmally low. What if we instead do 100 shots and we simulate that? It's going to crunch the numbers. We have an 89% chance of getting the right answer and a 77% chance of replicating it. However, what if we want to try and identify something as small as crosswind jump? And let's go back to 20 shots. We simulate that. We have a 5% chance of getting the right answer, a 2% chance of repeating that, and a 5% chance of getting actually the wrong answer. So maybe we need 100 shots. We try that again, and it only went up to 7%. What if we shoot 1,000 shots? This is 1,000 shots on paper, followed by a second 1,000 shots on paper, so we can compare those two scenarios. We have a whole 8% chance of getting it right and a 1% chance of repeating that. What if we shoot 5,000 rounds? Takes a second because this is a lot of simulation. We're up to a 10% chance of getting it right. Basically what this is telling us is these tiny effect size. For example, where did I put my target? For example, if you want to tell the difference between 26.5 and 27 grains of H4895 in your 6 ppc, we don't actually know the effect size of this, but it's probably tiny, and you probably need between 1,000 and 10,000 rounds of ammo to be able to identify this difference, not 5. I think that's everything I have to say. If you found value in this, please hit the like button so that we know that you enjoyed watching it and we know that you'd like us to make more. Alright, so the point of this was not that you have to shoot 100 round groups, although sometimes you do. The whole point of this is that we are trying to establish a scientifically sound model for understanding precision. So when we go and do tests, we can have high confidence that our results are significant. And when I say significant, I mean statistically significant, or more technically speaking, that P is less than 0.05. Yeah, so the point is that we need a model to predict why does every bullet not go through the same hole, and where we're trying to chip away at layer by layer, starting with the biggest ones, the mechanical precision of the gun or the error that the shooter introduces. When we're trying to measure that and test that, we need to be able to actually scientifically compare instead of just shooting a couple of 5-shot groups and measuring them and hoping for the best. If you have something to say, please leave an inflammatory comment in the comment section below. Thanks for watching, and we're looking forward to making more of these videos for you.